Hello everyone. Our today's A-level chemistry topic is oxides of period 3 elements. Now, period 3 elements are sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine and argon. These are their proton numbers. Sodium has 11 proton number, magnesium 12, aluminum 13, silicon 14, phosphorus 15, sulfur 16, chlorine 17 and argon 18. When we observe the electronic configuration in this third period, then we know that the number of electrons in the last shell increases from left to right. The sodium has 1 electron in its last shell, magnesium has 2, aluminum has 3 and so on. That's why from this it is quite clear that the removal of 1 electron from the last shell is quite easy. The removal of 2 electrons from the last shell of magnesium becomes difficult, 3 electrons from aluminum becomes difficult, and then 4 electrons from the silicon, it also becomes too much difficult. That's why we came to know that the metallic character from left to right in the period 3 decreases, and from phosphorus automatically the last shell contain more than half electron. That's why they will never lose electron. They will try to gain electron to complete their last shell. It means that they are totally converted into the non-metals. Now, if we discuss oxides, when sodium is burned in oxygen, sodium react with oxygen and burn with golden yellow flame, and the balanced chemical equation for the formation of sodium oxide is given just like this. Similarly, magnesium also burn in oxygen when it is heated, and it burn it with a very bright white flame producing magnesium oxide powder. Aluminium also burn with in air, producing a very brilliant white flame, and this produce Al2O3 aluminium oxide. Silicon reacts slowly with oxygen and produce silicon dioxide. Now, phosphorus react with oxygen and burn with white or yellow flame and convert into P4O10 phosphorus pentoxide. Sulfur burn in oxygen and produce sulfur dioxide on burning, and then catalytically sulfur dioxide is converted into the sulfur trioxide. Sulfur trioxide cannot be formed just by burning the sulfur. Now, next is chlorine. Chlorine react with oxygen also. It produce Cl2O. It can produce Cl2O5. It can also produce Cl2O7. Now, these are all the oxides. If we consider their structure, then oxide of alkali metal, sodium, is giant ionic structure it is formed. Similarly, magnesium oxide also form giant ionic structure, and aluminium also form a giant ionic structure. But silicon dioxide or silicon 4 oxide produce a giant covalent structure, macromolecule, giant covalent structures. Then rest of the oxides, P4O10, oxides of sulfur, either it is the sulfur dioxide or sulfur trioxide, or either the oxides of chlorine. All these are simple molecular structure. Simple molecular structure, small molecule, micromolecular structure. If we discuss the behavior of their oxides, the behavior of oxides to check either these are acidic or basic, or we use water. Water is a standard solvent in which by dissolving any substance we can check either the substance is acidic or basic. For example, when we dissolve sodium oxide in water, it produces sodium hydroxide, which is a very strongly alkaline solution is produced. But when we dissolve magnesium oxide partly dissolved in water rather remain insoluble, and it gives milk of magnesium hydroxide. Both of these magnesium oxide and magnesium hydroxide are used as an antidote for the stomach pain, for the acidity, and that's why this is also used. But these are weakly alkaline as compared to the sodium hydroxide. Why? Aluminium oxide is insoluble in water. It doesn't react due to the protective aluminum oxide black layer on the aluminium metal. So this will not react with the water. So it is not said that it is either acidic or basic. But by reacting, due to the reaction of aluminum oxide with both acids and bases, this is called as amphoteric. Aluminum oxide on reacting with sulfuric acid produce aluminum sulfate and water. And similarly, aluminum oxide also react with sodium hydroxide aqueous solution and produce sodium aluminate. This is also soluble complex of aluminium. As aluminum oxide react with both acids and bases, that's why this is called as amphoteric in nature. Now, from aluminium, silicon dioxide, as it is a giant covalent structure, if it is non-metal or semi-metal, that's why its oxide is acidic in nature. How it is proved? When we dissolve silicon dioxide in water, it is not dissolved in water, so its character cannot be understood. But when we treat silicon dioxide with a base, strong alkali, sodium hydroxide, it produces sodium silicate. It means that as this is reacting with very strong alkali producing salt, definitely its character will be the acidic. Next is phosphorus pentoxide. When we dissolve phosphorus pentoxide into water, it produces a phosphoric acid. It means that the nature of P4O10 oxides of phosphorus is acidic. Clear? When we dissolve sulfur dioxide and sulfur dioxide into water, both of these gases produce sulfurous acid or sulfuric 4 acid, and sulfur dioxide produce sulfuric 6 acid. Similarly, the oxides of chlorine also on dissolving into water decompose easily and produce respective acids of chlorine and also oxyacids of chlorine. It means that from silicon to chlorine, all the oxides of these elements show acidic character, and they produce either acids on dissolving into water, or they react with strong alkalis to produce salts. That's why these are termed as that these are acidic in nature. Now, if we consider the electrical conductivity of these period 3 elements, the sodium is conductor, magnesium is conductor, aluminium is also conductor. These are the metals. But this is a semi-metal or approximately non-metal. The conductance drops significantly in of silicon. And all these, phosphorus, sulfur, chlorine and argon, all these are the non-metal, so their conductivity decreases to 0. Similarly, the group 3 metal oxides show different ionic or behavior. If we consider the melting point of the oxides of all these, definitely as the alkali metal sodium is producing giant ionic levels, definitely it will show very high melting point. Now the melting point of magnesium oxide will be much more as compared to the alkali metal oxides. It means that from sodium to aluminium and to silicon, till silicon, the melting point of their oxides increases considerably. Why? Because in case of magnesium oxide, charges on cation and anion become double, force of attraction become 4-4. That's why the melting point of magnesium oxide is many times more as compared to the sodium oxide. Similarly, in case of aluminium, the strong force of attraction between cation of aluminium with positive 3 charge and between force of attraction between negatively charged oxide ion, the force of attraction is much more stronger. That's why the melting point of aluminum oxide is also very high. Both of these substances, rather all of these 3 substances, their oxides are said to be refractory material because their melting point are too much high. The silicon dioxide itself is a macromolecule. No doubt it has a covalent character, but due to the macromolecule, its melting point is also very high. But from phosphorus to chlorine, all these are discrete molecules. They will have very low melting and boiling points, obviously. And they also show intermolecular forces or van der Waals forces, due to which their forces are melting point are very less. Please, I have explained whole of the concept in case of the oxide of period 3. Comment, like, share or subscribe my YouTube channel. I thank you all.